I mentioned Trump because that's his, the next big building going in Chicago has 12,000, 6.6 million modulus of elasticity, high strength silica fume concrete all the way. I think it's 80 stories right now, but they keep changing the elevation. They keep that stuff secret. But what is high performance? We talked about high strength, high performance. You know, in the past, concrete was just, you know, concrete. And as I said, it failed in about 30 years. The FHWA describes high performance concrete as a concrete in which certain characteristics are developed for a particular application and environment. And the operative words in that sentence are certain characteristics. Strength is just one characteristic of concrete. There's a lot of other characteristics, and some of those characteristics may be these type things that we can make concrete very easily to place. Has anybody heard of self-consolidating concrete? They call it SCC. This is concrete that really you don't really place it or finish it. It flows like water, and all the aggregate in the concrete moves with it. In a precast yard, it's literally, in the last 5 years, it's literally revolutionized the way that they do precast concrete in the yard. Before they had vibrators and laborers and people striking off the I-beams and girders and those type things. Now they pour this concrete at one end of the form, it runs all the way down to the other end of the form, they're done. There's no vibration, there's no noise, there's no laborers climbing all over the place, and that's only in the last 5 or 10 years. That's a high performance concrete. This compaction without segregation, that would be the same thing. Concrete that would flow into place and move without the aggregate separating from the mortar. That's what segregation is, when everything falls apart. You want things to stay together homogeneously. Could be fast tracking. You may want the strength to happen very early, or long-term properties. Maybe you're building a structure like a highway or an airport that has 75, 100-year design life to it. Or a building. How long is the design life for a high-rise building? A couple hundred years? I don't know. Permeability or density. Density could be both heavyweight, lightweight concretes, depending on what your goal is. If you're doing nuclear shielding at a hospital or something, you may have some pretty heavy concrete. Low heat of hydration, mass concrete structures, real thick walls. This happens to be a combination of both. These are real thick walls out at the Hanford nuclear site in Richland, Washington. And they're utilizing both low heat of hydration and long-term properties. Obviously, they're still storing nuclear waste in there. They're going to be in there for a couple hundred years, so they're trying to keep that alive. This last website is actually a place for more information on bridges, part of the FHWA presentation that we do. But how do we make high-performance concrete? This is all the cementitious materials that we put in concrete. Cementitious materials mean that when you add water to them, they hydrate, they react chemically. The cement and water together become something different. The concrete doesn't dry out. The water is actually used in a chemical reaction. And we'll talk a little bit about that chemical reaction. These three powders, Portland cement, slag, and fly ash, class C, if you add water to those guys, they will hydrate, they'll get hard. They're cementitious. Silica fume or microsilica, and if I had F ash or class F fly ash, if I had another pile of that, if you add water to these two guys, all you made is dirty water. They don't hydrate. They don't hydrate at all. But if you go all the way back to what that first video said, where the guy said we stole stuff from the Romans, that's what the Romans actually used to build the Appian Way and the Colosseum and you know, their old structures that are still, that we go over there and visit. They used actually Vesuvius ash, which is pretty close to silica fume, with ground up local limestone, pulverized, and that's what they made their concrete out of. It was so popular that they called it, after the city where they got the ash from, the city in Italy is called Pozzolana. So this chemistry, this type of chemistry here with silica fume and this F ash reacting with lime is called pozzolanic chemistry. That's been around for 2,000 years. This chemistry, this Portland cement chemistry, is hydration of water. Portland cement was patented in 1824. 1824 in England. It's called Portland because the cement actually resembled the rocks on the Isle of Portland. It has nothing to do with Maine or Oregon. It's because it resembled these rocks off this island in the UK when they first came up with this product. So this chemistry here, this technology has only been around for less than 200 years. What we're doing here with high performance concrete is we're combining these two chemistries. We're combining this 200-year-old chemistry with this 2,000-year-old chemistry over here. I'll show you how all that works. A little bit about cement hydration, and I won't bore you too much because this isn't a chemistry class, but real straightforward. If we take cement or a reactive class C fly ash or slag and add water to it, it produces what's called a calcium silicate hydrate gel, CSH. That's actually the glue of the chemical reaction. When this goes forward, this is the glue that holds everything together. The cement hydrates, it grows crystals, the crystals interlock, and it gets real strong on a micro scale. That's only about 65% efficient at producing this glue. The other 25–35% goes at producing calcium hydroxide. Calcium's in lime. That's a good thing. About 35% of that goes at producing lime and then some heat. Well, what happens if we add a pozzolan to it, using that Roman technology? If we have the same cementitious materials together with water, and in this case we combine our pozzolan material, either silica fume or F-ash, what happens is this material reacts with the calcium hydroxide and converts it into more CSH gel. So it acts as a catalyst, if you will, of making this chemical reaction more efficient at producing the glue and less efficient at producing this calcium hydroxide. In concrete, you hear guys talk about free lime, my concrete floors dusting. If you look at mortar on some of the buildings, I haven't looked at the buildings around here, but if you look at mortar on bricks on the side of buildings, you can see white leaching out of the side and running down the side of nice pretty bricks on homes that spent millions of dollars on, and they got this stain leaching down the side of their bricks. That's this calcium hydroxide breaking down. That's the free lime coming out. It's a real weak crystal and it comes out of the cement. It's the reason why floors dust. It's the reason why mortar leaches. Pozzolans will tie that up and convert it into more of the glue that holds everything together. So normally when you add pozzolans to concrete, first thing that's going to happen is you're going to get real strong because you're making more glue. So you've got to balance out all this chemistry. But that's what happens on a chemical standpoint. This is a little chart showing the effect of adding silica fume or microsilica content and the reduction in the calcium hydroxide. You probably have to get about 28% or so silica fume in there to eliminate all of it if you really wanted to. Most people don't. What is silica fume and how is it produced? Silica fume, the name silica and fume, it's Latin for smoke. No fumar, right? No smoking. It's smoke. It's silica smoke. It's actually the smoke that's given off of open arc electric furnaces where 50 years ago, at least in this country, used to go in the atmosphere. This is silica fume. It is full. It's a full container. It feels like it's empty. It's captured smoke. It won't come out. You can take it off. You can take it off. It's fine. It's just real light. It probably has a bulk density of about 8 pounds a cubic foot. So a cubic foot of this, what's water? What's a cubic foot of water weigh? 60-some? 62.4 pounds. So this silica fume, it weighs about 8 in that container. That's actually captured smoke. In the past, it used to go out this stack here. What they do now is they pull it down the stack with fans and run it through filters. And when it comes out this filtering system, that's the material that comes directly out of this filter. It's so light in that condition that you really can't use it. The people that produce this material for concrete, they actually densify that material up to about 40 pounds per cubic foot so that it can be handled in trucks and blown around like cement and handled pneumatically. But that's the original material. I wanted to show you the lightness of that material. I won't throw this, but this is actually the silicon, the Si, that comes out of the bottom of the reaction. They take quartz, coal, wood chips, and coke and smelt it all in this open arc electric furnace, and they're trying to get the Si, they're trying to get the silicon out of the quartz. That's what they're tapping out of here, and that's the element that I'm passing around here. That's element number 14, I think. Element number 14 on the periodic chart, Si. The smoke, as it goes up the stack, is a gas. It's an SiO gas. And it combines as it cools somewhere around 600 C. It combines with another oxygen and forms a solid.